All right, so we're going to look at Doppler effect, right?
Mm-hmm.
So tonight's class is about Doppler effect, and it starts off with,
Is Magdalene going to be unavailable today?
yeah, she wasn't feeling well, so
I see. Oh, yeah, they gave me this new book, by the way.
22nd August. Did you get that from school? All right, that's great. That's great. So this starts off with waves, right? The long and short of it is that waves.
Today, Mr. P,
Yeah.
since it's just me and you one-on-one,
Mm-hmm.
I don't want a mistake with Doppler effect, because I heard it's an easy thing to learn and
Yeah.
master, but then I don't want to master it in a concept where I have to walk 10 kilometers to get to the shop when I can only take 2 steps.
Okay, so we'll find the shortest way to get the concept. It's
Yes. And
I understand.
you know what I was suggesting with Doppler?
fine.
Does it have formulas?
It does have formulae.
So formulae.
We need to first understand the key concepts. Then when we understand the key concepts from the properties of waves, we will understand how to apply the formula.
Okay.
And we also need to understand vibration, so that we can, place that concept in both sound and light.
Okay.
Yeah.
I understand.
So let's start off with vibration.
I'm starting with waves.
Vibrations cause waves, and waves also cause vibration, right?
Does frequency fall under vibration?
Yes, it does, and we will understand how that works as we continue with the thing. I like the questions that you're asking. It shows you engage in the content.
I told
So
you that
vibration-
I'm balancing myself. Change.
That's good.
Today when I left home, my
Mhm.
mom told me that if you want to change, you cannot do the same things that you do and expect something different.
Yes.
So, from what I understand from that was that you wrote H.
Vibrations are caused by waves.
Is it this?
Oh, it's supposed to be a T and an I.
That's why I said you wrote H.
Vibrations. So, what this tells us is that these two, waves and vibrations, cause each other. Each one is a cause of the effect and also an effect to the cause.
Can
So-
I get the mouse?
Mouse, all right. So, everything is vibration.
Oh, she joined.
Yes. Hi, Magdalene. I just save you. Oh, Magdalene's already in, so just click there so she can see our class. And then press there to share screen, and then share that one.
Oh. Let's share.
Yeah. Welcome, Magdalene. All right. How are you feeling today? Hmm?
She's worse.
Are you feeling worse? Will you be able to focus during class though? You will try and focus. All right. This topic is going to touch a little bit on waves. You've come across waves and light before, right? All right, so we're going to do a little bit of revision there. And we start with waves and vibrations. So waves are caused by vibrations, and vibrations are also caused by waves. Now, what does this mean? When you are making up your bed, and then you shake the duvet or the blanket so that it will shave rock. You're removing the sleep and the evening from the blanket so that you make up your bed. So it kind of does a wave-like motion, right? So that wave causes a vibration. Like if you were to have a very long blanket, it would continue like that and it will ripple. Another example, when you are in a bathtub or you're doing your laundry and then you put the bathtub there and then it's full of water. When the water is still, it's not moving. If you put your finger at the top of the surface in the center, you'll see ripples, right? So let's say this is our Vascom.
Before we push into deep, I want to know which one comes first. Is it waves that comes before vibrations, or vibrations that comes before waves?
I would like to think it's a chicken and egg type of thing. Where which one came first, the chicken or the hen? Sorry, the hen or the egg? Because the argument is without the egg we wouldn't have a hen, and without the hen we wouldn't have an egg.
So they correspond with each other?
They correspond, yes. Okay. They correspond.
One cannot exist without the other.
One causes the other and the other is caused by the other. Yeah. So when your bathtub is full of water and you sort of dip your finger there.
Aye, that water looks cold.
And then you get ripples, right?
Mm-hmm.
And then you get ripples.
Nice ripple animation.
Thank you. Yeah, so this is a better illustration. So this is a tub filled with water. Ne? And then you stick your finger there in the middle. I'll just draw a hand like that. So let's say your hand is there. And then you get ripples, right? So...
Mind making it dark? Mind making the hand dark?
Like I should color it in?
Yes.
Okay, I'll give it my complexion. So that's
Mr. P complexion.
Yes. Yeah. All right. So our bathtub, we dip our finger in and then we get ripples, right? Mm-hmm. So these waves are caused by a vibration. So at the point of contact where the finger touches the surface of the water, you get a vibration. And now that vibration ripples out and carries on in that direction across the surface of the water.
Do the vibrations have a range?
I guess it depends on the like qualities or properties of the waves themselves. So the amplitude, for example, of the ripples, those would, range between a certain amplitude and a wavelength, etc.
I have a big pool of water, and then I just dip my finger at the center.
Yeah.
Will the waves cause vibrations that stop at a 5-meter radius, then dissipate, or will it go on until it meets something solid? Okay.
That's a good question. I actually saw a video of what do they call it? Wave. What do they call it? This thing. China wave river opens into ocean. I forgot what the concept is called. Tidal bore. Yes, a tidal bore, right? Mm-hmm. So I'm gonna let's open it up here. Let's open it up here so that Magdalene can also see. Yes. So let's type in tidal
bore.
Bore
For the animal, barbarian.
Tidal bore, China. They had this beautiful video of a tidal bore in China, and yes, I don't know how to pronounce this. It's Qiantang River. Okay. So let's share this video using some else. I don't know why it's showing that ad.
That's why I started laughing.
Okay, so this here shows us waves, right?
Mm-hmm.
And so depending on, so waves in the ocean are caused by I think seismic activity underneath the surface of the ocean.
Yes, when the rock overfalls on another one.
Yeah, with
Like,
geological faults.
Then
Yes.
the idea wave.
Yes. So that shock, that energy from the slip of the faults
Mm-hmm.
causes then it sends a shock wave from the surface of the earth underneath the water, and then that shock wave ripples out towards the surface of the ocean, and then that drives the wave motion, and the wave motion goes from all the way in the middle of the ocean somewhere to the shore, the shoreline, right?
That's what I wanted to know. Like, if it happens at the center, will it reach the shore, or will it go on for a certain distance then die out?
Again, it also depends on the amount of energy, I suppose, in the shock wave.
Mm-hmm.
Yeah. So let's say the seismic activity happens way too far in the ocean and it's very small.
Mm-hmm.
It could, let's say, create a wave. Now, if that wave doesn't have enough energy to reach the shore, it'll just die out.
Okay.
But if it's big enough, like in a tsunami then that could have a significant effect that it can even destroy the ocean. Sorry, the shoreline or whatever that you have by the coast.
So, here's another question.
Yeah.
There's a wall.
Mm-hmm.
The wave starts. It hits the wall. Will it rebound, or will the wall absorb the energy and it'll die out?
All right. I like that question because that's kind of what happens when you, in this scenario here, these ripples, in fact, you would see it nice if your surface was square or had a different geometric shape instead of a circular or elliptical shape. So you'd see these ripples go in that direction, and then when they hit the surface of the walls, they'd also go back in that direction, and they'd do a back and forth like that. Back and forth between the center, the origin of the waves, and then like that. So from the center where they start to the wall and then back again. So you would see the waves like that, right?
So the energy cannot be absorbed by the surface.
It's reflected. Yeah, it's reflected. So it's sort of like, I guess waves behave like that whether they are light or sound, because light is also a form of wave. Yeah, it's just at a different wavelength that we can't see
with the naked eye,
but it doesn't mean it's not there. Because, yeah, and I think that's what's also explained by the topic of, what's this, photons and stuff that reflect light. So then the particles would then be what we are observing.
Hey, spot betting, you want to bet.
So yeah. So that's then our topic there on waves and how we can sort of discuss them in natural phenomena. So there are two types of waves. Ne? The first one is transverse. And these look like your car's sine graphs, ne? And they are like this. And then we have longitudinal waves. Longitudinal waves, ne? And longitudinal waves have parts where they experience compression and parts where they experience refraction. So I'll just do something like this. So this would be a representation of longitudinal waves. So in both cases, let's assume the direction of motion is from the left to the right. So the wave motion would be illustrated as follows. And that would be the wave motion for a transverse wave. So above, this would be the wave motion for a transverse wave. Our wave travels from left to right, and our longitudinal wave travels from left to right, and that would be the direction of the wave motion. Now, if we have a particle, let's say we're looking at those ripples on the surface of water, and we're looking at a particle of water it'll move from up all the way to down so from the crest to the trough, again to a crest, and then again to a trough.
My apologies, you said that the wave motion moves from...
let's assume that it moves from the left of the screen to the right of the screen.
Is it always the case, or can it start backwards?
It can start in any direction, but for us to just understand how the waves behave, we'll just assume for this particular instance that the motion is from left to right. Right? So our particle would be moving up and down, and would illustrate that to say particle motion happens in this direction. So that would be the direction of particle motion. Yeah? And with longitudinal waves, the disturbance of the medium is parallel to the direction. Oh, we'll get to that. So with longitudinal waves, the particle would move in this direction. So let's assume we're listening to sound, right? You know, when you're in a taxi, school transport, you're in school transport, and it's those ones that are notorious for having sound systems that vibrate the windows of the of the neighbor. So, and it goes. So if we think about a particle of air, when the sound comes from the speaker, the particle of air would be somewhere there, and it will move from, let's say this is where the speaker comes from. Sorry, the sound from the speaker comes from. Then the particle of air would move from there to there. And supposedly back and forth in that direction. Examples of transverse waves include water waves, so ripples. That's the obvious case. Then also electromagnetic waves, right? Electromagnetic waves. And these also include light, radio. So exactly the same radio in our households, FM, like the FM radio, right? So radio waves and X-rays, ne? And it's important when you look at the dial of a radio, for example, there's always like Thobela FM. Do you know the frequency modulation of Thobela FM, which is a popular radio station here?
I'm not aware with Doppler Effect. I'm actually aware with Morau FM.
Morau FM. Do you know what the frequency modulation is?
Yes.
What is it?
9.25.
92.5 megahertz. So 92.5 megahertz. So hertz would be the frequency, right?
Yes.
So that's the frequency that one single wave.
Hertz is the measurement of frequency, right?
Yes. So in other words, how many times one wavelength repeats itself, right? And we will discuss the unit of hertz in this class, okay? And then examples of longitudinal waves include sound waves, again, speaker in the taxi, guys playing shebeshiti, they're collecting school kids, or dropping them off during assembly while he's still playing.
He's alone in the car.
No, and some amapiano beat or some, you know. And there's also a slinky spring. So that slinky spring that looks like it's colorful and, or, you know, think about your spring inside your click pen.
Mm-hmm.
That slinky spring looks like that.
The one that spirals.
That spirals, yes. So we'll just write there, slinky spring. That's an example of a longitudinal wave. Okay?
Mm-hmm.
Other important properties of transverse waves include that the disturbance of the medium is perpendicular to the direction in which the wave is propagated. So the wave is propagated from this direction, left to right, but the disturbance of the medium is perpendicular. So in other words, the particle motion, which is indicative of the disturbance of the medium, is vertical, whereas the wave moves horizontally.
Mm-hmm.
But with longitudinal waves, the disturbance of the medium is parallel to the direction of motion of the pulse. So sound comes off as pulses. That's why we feel some vibrations.
Mm.
Yeah, like I know a business owner who ran a nightclub he wasn't hard of hearing, but his hearing was a bit limited.
Oh.
And one of the things that his condition allowed him to experience was that if he wanted to assess how good the sound quality was, he would feel the vibrations of the sound on his skin. And I guess like touch is a very good way of also feeling some sensations.
Okay.
So because sound would pulsate if he's in the vicinity of the speakers, for example, he'd be able to tell the quality of the bass, for example, from the quality of the other higher frequency sound elements that come from the sound system. So it's not to say he was an expert, but if he wanted to make a call on whether or not he made a good investment in the speaker system, for example, those are the things he would look out for, because he would listen to the pulsation. And that pulsation is this distance here. So where you have a compression and a rarefaction.
Even cups, I believe, are good indicators of whether sound is good quality or not.
Cups?
Yes, because like most of the cases, from what I learned from the nearby tavern owner at my house, he said that if he wants to hear that his speakers are good, he holds the cup like this at a low point. If he can feel the cup vibrating, that means the sound is good to him, and which is true, because it actually works. In most cases, when I'm in class with a bottle of water, if the teacher is speaking at a level of which everybody can hear him, I can feel the bottle of water get sort of so I hold it down to my legs. It must vibrate. As soon as it vibrates, he's audible to everybody. There's no person who can say alcohol.
That's very interesting. Thank you for sharing that. It's quite an interesting way of also interacting with the elements. So the interesting thing is that, and this is not Bible class, but a lot of things start with sound, right? You have to, so a lot of things start with sound. Like in the Bible, it said in the beginning there was the word, and the word said, "Let there be light." So sound came before light.
Let there be light.
Let there be light. So not to say this is Bible study, but I just think it's an interesting thing to think about.
There's a male mosquito in here.
How do you tell it's a male?
It bumps the skin.
Oh.
A female goes straight for the kill. Like, you bump no fitla ya do. But then the male, it bumps
just
and leaves
bumps.
the scent so that the female can come and
come.
pick you up.
Oh, that's an interesting hunting strategy for mosquitoes.
Because only males can suck, females can suck.
Can suck, yeah. That's what I know. I just wasn't aware of that, but thanks for sharing. But anyway, back to wave properties. Yeah. So wave properties are as follows. Let's say we have a transverse wave and it goes all the way in this direction, right? So we're going to draw a wave that looks almost like a sine wave from trigonometry, right? So that's the first part. The second part. Okay, let's just do that. So just do 2 parts. All right, so we don't know where the wave starts and where it ends, but we'll just truncate or cut somewhere between there and there, right? So if we look in the y direction or the vertical direction versus the x direction, if we start off by looking at the y direction, then this tells us about the displacement. So we'll just put that there, right? Displacement. And then that's measured in the vertical direction. And somewhere between the axis along which we measure the distance traveled, which is the x direction, somewhere between there and the crest of each wave, we would get the amplitude, right? So amplitude simply means height. So amplitude. All right, so then the distance between 2 crests we would call the wavelength. So in other words, how long the wave is. And when we have a complete cycle, which is from that point to that point and again to that point, we have a complete cycle, right? So this would be a complete cycle. So this would be a complete cycle. And so this here would be the distance traveled. Okay, so amplitude would be height, which is the maximum displacement of particles from equilibrium position. So here, this would be equilibrium position. So that's why we neither have displacement in the positive upward direction or negative downward direction. That's the equilibrium position. So amplitude is the maximum height in either direction, right? So above the equilibrium position would be positive and below would be in the negative direction. Then wavelength would be given symbol lambda, and it's the distance between 2 consecutive points in the wave which are in phase and is measured in meters. So let's say position between 2 crests, or rather distance between 2 crests.
Is that the symbol for wavelength?
Yes, it's lambda.
Lambda.
Yes, lambda.
I wonder who came up with that.
It's a Greek symbol. So on the Greek alphabet, it's one of those that are on the Greek alphabet. So distance between 2 crests. So crest being that point. And it's measured in meters. Measured in meters. M. And then frequency. Now this is where, remember we spoke about rather, when you tune into a radio station and it's 92.5 megahertz, this is where frequency comes in. So frequency is how often something occurs, right?
Yes.
We also learn this in is it in stats or probability? One of the two.
How, what?
Frequency.
It's stats.
Stats.
It's called the mode.
Mode, yes. So how often something happens.
Yes.
So let's think about these waves, ne? So the first wave starts from here and it cycles like that. Then it repeats again and cycles like that. Then it goes on and on and on and on and on and on and on. So each time it does that, we have a complete wave, another complete wave, etc. So within a certain distance that we can observe, the number of times that wavelength happens, that's the frequency. Right? So it is the number of complete waves passing a specific point per second, right? So number of complete waves. Complete waves being starting from rest position to a crest, back to rest, below the rest position, and then back again to rest again. So that's a complete wave.
Okay.
It repeats again, it repeats again, it repeats again. Then you have 3 complete cycles. So that 3, if it happens over a certain amount of time, that's the frequency. So number of complete cycles, passing a specific point per second. A specific point.
Oh yeah, I remember something, but then I'll tell you after class.
Per second, okay. All right. So the frequency of light waves determines its color. And this is important because violet would have a much higher frequency than red. Yes.
Violet.
Yes.
Like
the color violet, that one?
Yes.
Would have a much higher
frequency. It doesn't
frequency.
qualify as purple violet though. They say that it's a mixture of light purple and red.
And red.
Yes.
Okay.
Since there's the fact that it's light purple, it obviously has a weaker frequency compared to red because red is condensed. Is it blue and yellow? Green and yellow. No.
The point is, with colors, we've got red, orange, yellow, green, blue, indigo, and violet, right? So on this end, we'd have low frequency, and on this end, we'd have high frequency. Yeah. So in your new age, inverted commas, in your new age beliefs, then that would be your red colors, which represent root chakra, and it would be represented with red. And this would be crown chakra, which would be represented with violet. And the lower ones would be towards the base of your spine, whereas the higher ones would be towards the crown of your head. Yeah, so that's like I said, new age beliefs. It's not against spirit class, but it's just an association you could make if you're open to that.
Yeah.
I'll
take it into custody.
All right. So with light, the frequency determines its color. So frequency determines color. Okay, and the frequency of a wave determines the energy of the wave. There's a saying that is attributed to Nikola Tesla. I don't know if it's true that Nikola Tesla said that, because on the internet people say so-and-so said that, only to find that someone else said it, But anyway, let's just say this was said by Nikola Tesla as he is attributed with it, right? And the saying is that if you want to understand the universe, then think in terms of energy, vibration, and frequency. So that...
Let me just be quiet and take that.
Yeah.
Because
so,
it's true
so
that
the
someone said that, but then it's not Nikola Tesla.
Yeah, it could be true that someone said that. I mean, we have heard the saying, but the point of that, I believe, has to do with the fact that all matter is energy vibrating at different rates. So solid particles, for example, are a denser form of matter, meaning the particles are vibrating but at a slower rate than air particles, right? But also that means if we think about particles in wave form, then solids would be at a low vibration frequency, whereas light would be at a faster vibration or higher frequency. You know, that type of thing. And the vibrations would also therefore be different like that. And the energy state. So to solidify something, you'd have to cool it or dense it down. For example, water, to turn it to ice, you have to take out as much energy out of it as possible by refrigerating it to a point where it's frozen. And for it to be boiled, you have to invest amount of energy to heat it up so that it can be water vapor. Yeah, so if you think about it like that, then it kind of makes sense, that say.
Water vapor particles moving at a high frequency.
They have a higher state of energy. Yes, so they are also moving at a higher rate of vibration.
I get you.
So the higher the energy, the higher the frequency. In other words, energy is directly proportional to the frequency. All right. Now, we're going to look at another concept, or more concepts. And wait, are we still sharing this screen? Oh, okay. Magdalene, we're still together, ne?
Oh.
Yeah. Got the complexion. Well done. Well done. So there's another concept called period, ne? There are other types of periods, like in class, we have a period for maths, we have a period for science, we have a period for English, right? But in this case, the period, symbol capital T, of wave motion is the time taken for one complete wave to pass a point, right? So it's the time taken
for one wave,
for a wave, yes, to completely pass a point, a fixed point, right? And another thing is that, remember frequency, F is the number of waves passing a point per unit time, right? So number of waves passing a point over a period of time, right? Or over an amount of time. Let's do this. So this means frequency is 1 over the period, and this means period is 1 divided by frequency. Okay? Then the other one is the speed. And I think it's important that the speed or wave velocity...
Frequency is number of waves passing a point divided by the amount of time.
Yes.
But then you said F equals to 1 over T. So,
F equals 1 over T, yes.
So meaning that 1 is the number of... I get it. Yeah, I'm still with you.
We're still together. All right. But you can say what you just realized so that, I mean, I also get to understand how you're thinking about the concept.
Oh, I understood that this one is actually the number of waves passing a point, which means it's one wave passing a point. Or could be a wave passing one point.
Yeah. And it could be, let's say, if it's a higher frequency,
Mm-hmm.
could be several waves passing a point, depending on how the...
Do we count the waves or do we count the points it passes?
No, we count the waves.
Okay.
We count the waves. So frequency would then be in units, it would be seconds to the power -1, and that would be hertz. Yeah?
Mm-hmm.
And I believe hertz comes from the discoverer, so to speak, of hertz unit. Yes, not car rental. No. Right. So hertz is the System International unit of frequency, and its base unit is second to the power -1, and it's a reciprocal of a second, and it's named after Heinrich Rudolf Hertz, the first person to provide conclusive proof of the existence of electromagnetic waves. Now, for high frequencies, this unit is commonly expressed in multiples of kilohertz, megahertz, gigahertz, and terahertz. Megahertz being that which are used in radio frequencies when we are tuning into a radio station.
Mm-hmm.
Okay.
When are gigahertz used?
Gigahertz. Interesting. Let's see.
The female came in. Yeah, I did.
Gigahertz. Oh, gigahertz are used in computing.
Mm-hmm.
For example, IBM Power microprocessors are designed and sold by IBM for servers and supercomputers. The name Power was originally an acronym for performance optimization with enhanced risk, and it's been used. Okay, so yeah. So from 1 megahertz, you'd find certain computers, and then gigahertz also in computing, that's where you find gigahertz. Okay. Then back to speed of waves. Yeah. That is the rate at which energy is propagated by the wave. Ne?
Mm-hmm.
Rate at which energy is propagated by a wave, and it's measured in meters per second. I guess just like speed, and this would equal frequency times, frequency times wavelength. Okay, I thought maybe I used in the previous slide lambda as frequency, so I was correct in the previous one. So just to analyze these units, this would be meters per second.
You use lambda in wavelength.
Yes, in wavelength. So this would be inverse seconds, and this would be meters. So of course, when you multiply meters times second, then you get that unit. Yeah, so again, this is hertz, and hertz. So this would be wavelength. This would be frequency. And this would be speed. Okay, so again, hertz. It's named after who? I forgot the name now. Heinrich Rudolf Hertz.
Heinrich.
Yes,
Rich.
Heinrich
Heinrich Rudolf Hertz.
Hertz.
Mm.
And
He lived in the 18s actually.
in the 1800s, so from 1857 to 1894, and he is the one who provided conclusive proof of the
He's
the first person, yes, to provide conclusive proof of the existence of electromagnetic waves. So the wording, I think, is very clever, because it's not to say he discovered it, because
That's
how
why
do
I
you
corrected you and said the first.
Yes, so how do you discover that which is already there? You can't. But if you can demonstrate beyond reasonable doubt that it exists, then yeah, it makes sense that the unit was named after him.
Yeah.
Yeah. So, okay. Then we look at light. It's getting interesting now. Let there be light, right? You guys know the experiment done by Sir Isaac Newton with a prism. By the way, I believe, and I'll be corrected on this one, I think it was during a lockdown in the time of Sir Isaac Newton that he came across this experiment and he conducted it, where in a dark room, he shone white light
That passes the prism and created rainbow colors.
and split the, yes, diffracted the light into different colors. Yes. So a beam of light would be shown to the one side of the prism, and once that happens, the colors would split, and you'd start having them there. So the red would be on this side, and the blues and violets would be more or less on this side.
I got a question. So
Yeah.
with this prism and white light being shot and creating rainbow colors,
Mm-hmm.
if the rainbow colors are shot the opposite direction, will they create a white light?
That is interesting. I believe there is an experiment where if you take the three primary colors, red, green, and blue, and you make a disc. Okay. We'll do this experiment someday.
Okay.
But you have the disc and it's got red. So let's say it's got red. It's supposed to be a third. So it's got red. It's got blue. And it's got green, right? And let's say you color it on both sides, right? And then somewhere there, you put holes. And through these holes, you run strings, right? And then you twist the strings and then you pull it. So this disc would now spin. Doesn't matter the direction, but it spins so fast. So it spins so fast that the colors combined would turn white. Yeah, it's an experiment.
I've actually seen that experiment. I compare with it.
You've seen the experiment before. So I believe then because of that, it is possible that the reverse is true.
I mean, you cannot know if something's correct if you cannot do it backwards and get back where you started.
Okay, fair enough, which I believe we do that also a lot in math, where if you're going to factorize something, you got to be able to put it back to what it was originally. So yeah, I mean, it's interesting how you think about it, because then it shows how, all the other stuff connect. All right, so limited with colors there, but the point is there we have a prism. I saw this other meme. What did they say? Where do light particles... Oh, what happens to light that's gone bad or that does bad things? And then they say, oh, it gets sent to prison. And they get offered a light sentence.
Now that's a good one.
So yeah. So yes, this is what happens with light. So the visible spectrum of light is a small spectrum of a much greater series of wavelengths, and this is called the electromagnetic spectrum, right? So we have the electromagnetic spectrum. Again, thank you, Heinrich Rudolf Hertz, for establishing that electromagnetic waves exist. Now, the speed of light and all other electromagnetic radiation is constant, right? It's 3 times 10 to the 8 meters per second. That's quite fast when you think about it. Speed of sound, I believe so this is for light and electromagnetic waves. But for sound, I believe it's 330 meters per second. And you can also use this to calculate how far lightning struck from where you are during a thunderstorm.
How can you tell that?
You also have to take into account how many seconds between seeing the lightning bolt and hearing the thunderous sound. Because there's a lag between the two.
Yes, the light is faster than the sound.
The light happens faster than the sound, yes, because it's electric energy, so it's more rapid.
Why isn't it photons?
Well, photons, yes. So we'd see them much quicker than we hear the sound.
Yes.
Yeah. So because of that lag, if you count a couple of seconds after, then you can work out the distance. Because you have the time and you already know the speed of sound. So yeah, that's how you'd work them out.
Speed of sound.
Yes. So then the color of light depends on its frequency, and red has the longest wavelength and lowest frequency. So
I have a question.
Yeah.
With a lightning bolt, we can, from a far distance, you can see the light before you hear the sound.
Yes.
Why is it that with a gun, you hear the sound before the bullet? Or is it the bullet before the sound?
I think it still works the same. It still works the same as with lightning. Whereas, because the amount of energy that shoots the bullet out is so high, you would hear the bang after the bullets left the barrel of the gun.
But you can't see the bullet.
Yes, that's how fast it's moving. It's moving past the barrier of the speed of sound.
So the barrier of speed of sound is what, 200 miles?
It's 330 meters per second.
Which is to what, 200 miles?
Let's convert that to meters per second. So convert 330 meters per second to kilometers per hour. Magdalene, do you know how to convert between meters per second and kilometers per hour? Okay, so 330 meters per second is like 11, or rather 1,188 kilometers per hour. So the bullet travels probably a lot faster than that.
I thought bullets only travel at 200 miles per hour.
Nah, they travel much faster than that. They travel much, much faster than that. So, but anyway, we'll get to sound. But here's how to convert from meters per second to kilometers per hour. So 1 kilometer is 1,000 meters, and 1 hour is 3,600 seconds, right? So if we have 1 kilometer per hour, it should equal 1,000.
0.1 kilometers is what in meters?
0.1 kilometers. It's 100 meters.
Okay.
So 1 kilometer per hour would equal what's this? It would equal, so that would be 10 divide by 36. So 0.27 recurring kilometers per. Oh, no. Meters per second. So that's 1 kilometer per hour. Ne? That means if we want to convert meters per second to kilometers per hour. Now, I want us to picture, we know the fastest many cars can go is like 200, 220, 240, 280, 260 kilometers per hour, right?
550.
550. Which car is that? Bugatti. Okay.
Okay,
let's go with the fastest car on land.
Koenigsegg.
Wait, Koenigsegg. And how fast does it go?
I get 650.
Okay, but that's not the fastest car. The fastest car was tested in Karoo in Northern Cape. And let's go with that speed.
Check it right now. Say fastest car, you'll see. It's gonna say Koenigsegg. It might not be an Agera one.
Nah, I dispute Koenigsegg. I know Koenigsegg is fast and it's quite very fast, right? But the land speed record is the Thrust SSC.
The Mercedes-Benz can do better.
So 1,227.985 kilometers per hour, right? That's the fastest car.
That's why it's a supersonic car.
Yes,
you
this
don't
was
count
tested.
That. It's cheating.
No, but it's the faster that human can make something move on land. So let's go with that.
Okay.
It's the faster that humans have been able to make something move on land. And I believe it's been tested, I think it was tested in South Africa. In the Karoo. Yes, I promise you, there was something like that. It's called, what was it? Or maybe I just love South Africa so much, eh? But I promise you, there's something that was, there's a car like this that was tested here.
I only see the US.
I mean, it could have been done by a company, manufactured by a company outside of South Africa, but tested on South African soil.
Mercedes-Benz T80.
Okay, but you know what? Let's cut the debate. Let's just go with how fast this car moves. Ne?
Okay.
1,227.985 kilometers per hour. Ne? That's the fastest land speed record. Land speed record. Ne? Right, so we know that speed of sound is, this is 1188 kilometers per hour. And we want to compare how fast or slow land speed record is to speed of light and to speed of sound. That's what we want to compare. Okay. So land speed record is that. So obviously land speed record is faster than the speed of sound. Because 1,227.985 is greater than 1188, which is the speed of sound, right?
Wait, I'm trying to remember something. Yeah, I concur with it.
All right, so...
Because in 1873, the Mercedes-Benz T80, like, as soon as it reached 5 meters to the finish line, where it left is where people started hearing the sound. It started from here to here. Once it reached here, the sound was starting from there.
From there, yeah. So it broke past the speed of sound, meaning then there'd be a sonic boom, and you'd only get to hear the sound after you've seen the object.
Yeah.
Yeah, which is a similar phenomenon to lightning striking, and then you hearing the sound after you've seen the lightning bolt.
And airships, airstrike airplanes, I think. The fighter jets, yes, fighter jets. With a fighter jet, you can be looking at it, it can't move, but then the sound is there.
And we tend to see that quite a lot more Polokwane, because we're not that far from Hoedspruit, and our air base is in Hoedspruit. So you would see the jet over there and hear it like a couple of seconds later. Yeah, so speed of light is 1 million. No, wait. What?
Yeah.
speed of light value in meters per second.
I was already aware that it's over 1 million. Sometimes it's 200 million or 99999 million.
It's 1369. So 1 billion. No, we gotta get a second.
Ah, no, I do not concur. Check it again, Mr. P.
Nah, that's too big, ne?
Okay, check the original speed of light. Just say speed of light.
Okay, speed of light in meters per second is...
No, just check it. Just say speed of light. It'll fail, and then we'll convert it.
Look, speed of light is 299,792,458 meters per second, right? Which is literally 3 times 10 to the 8, right? So it's 1, 2, 3, 4, 5, 6, 7, 8. So 2.9 times 10 to the power 8.
Wow.
So 3 times 10 to the power 8. So if we're going to convert that, remember,
me on my way home at light speed.
So 0.27 meters per second is 1 kilometer per hour. So if we are to convert that from meters per second to kilometers per hour, the 3 times 10 to the power 8 from meters per second to kilometers per hour, it could be that big. So let's go with that. So it's 1.08 billion kilometers per hour, right?
When you get so rich that people think you're a millionaire, but you're just working hard to become a billionaire.
So 10 to the power 9 kilometers per hour, ne? That's the speed of light. So you'd have to travel at 1 billion kilometers per hour to travel it as fast as a photon. The speed of light.
So if you have to vibrate for your molecules and matter to be so fast that you can pass through solid objects, I have to be vibrating at what speed?
Yo, quite high, but here's the thing, that Einstein equation E equals mc squared then defines how if something has physical mass but it travels at the speed of light squared, it becomes energy. Yeah, right. So it's a very, very, very high rate of movement. It's a very high rate of movement. Also, but anyway, another interesting thing about the light spectrum that we're reading from our textbook, right, is that the spectrum of light is just a small section of a greater series of wavelengths called the electromagnetic spectrum. So what we see with our eyes isn't all there is to see. It's only a portion of what else is there. And I'm not sure about the percentages, but it's quite small. So everything else that is out there that we can't see is there. In the movie Lucy, there's a part where she shows the scientist something. I'm not saying that science fiction justifies science, but it's an interesting thing to think about. There's a part where she shows a car and it's moving, right, at normal speed. Then they accelerate the car to the point where it starts moving so fast that you start seeing just a blur. And then beyond moving a blur, you start not seeing the car.
Yeah, but then it's still there.
So then the question was, just because we don't see a car, does it mean it's not there? So if we're not seeing something, what does that tell us about what else is not there? How fast is it moving? How fast is it vibrating?
This is now a question I ask for ghosts.
We could go that far.
Is it moving fast? Or is it just intangible?
Or interdimensional beings, or even amadros. Or even ancient gods or whatever. It could go that far, but anyway, let's keep it to science in the material realm, which we understand. Otherwise, we'll go crazy.
Let's not push our luck.
Right. So anyway, the red spectrum is long wavelength, low frequency, And the violet wave end of the spectrum would be
Mr.
short
Piazza, so
wavelength.
which color do you write?
Which color do I?
Yeah, do you write? There are two different types of colors to write them, actually. There's UK English color and US.
Oh, you mean the spelling? I
Mm.
prefer the South African one because it's based on the British one.
Does it have a U?
It has a U, yeah.
My teacher does not allow that.
Why?
I don't know. She says that we should just use the one without a U. And I'm always
American frequency. American spelling.
Pronunciation.
Where's she from? Or they from? Or he?
They're from South Africa.
I mean, it'll be a matter of preference, but as far as I know, we use mostly British spelling. Except for words that are authentic South African, like Vuvuzela and Spikos. And, you know...
Bunny chow.
Yeah, you know, and...
Like, it
and
literally
Vascom.
has a bunny in it.
I mean... So personally, I wouldn't care as long as the message is
Clear.
Is clear. You're speaking about color, you know.
Uh-huh.
But I'm used to writing. The spelling with the U. Yeah. Then, okay. Now on to Doppler effect. So Doppler effect, long and short of it. So the Doppler effect of it, long and short of it, we're here in class, and then we hear that quantum that's delivering school transport, ne?
School learners.
School learners to school, and it's playing the track that's trending right now. It could be Shebeshite, it could be Kabza is Small, we don't know. But it's going... So we hear it from way out in the distance before it passes the point where we are.
Mm-hmm.
So we are here in class. There's Magdalene and there's Mr. P teaching on the blackboard, right? We're in the class, and then the quantum is traveling there. It looks like a loaf of bread.
Bruh. I'm looking at it, I'm like, is Mr. P trying to draw a loaf of bread or a quantum? Because I'm getting hungry.
And it's playing that favorite jam of ours, you know? Playing that favorite jam there. Right? Yeah, Barkimang, Master KG, and who's this lady with a very hypnotic voice?
Hypnotic. Let's leave her alone.
Okay, it's melodic. Let me say melodic.
Yeah.
It's very melodic.
That one I compare with.
What's her name?
Kazi, huh?
No, not Makazi. This one, Kosazana Dot.
Oh.
It's melodic. And then the quantum is passed and it's there, right?
Mm-hmm.
So let's say it's somewhere there. All right. And
This quantum is a transformer. It changed the wheels out of nowhere.
yeah, it's just to show yeah. Okay. So somewhere when it's making its way to our direction, we sort of kind of hear the sound in the distance, right? And the sound also sounds different to, like when it's here, the sound sounds different from when we're here as it is when it's there. And the reason for that it's what we call the Doppler effect, right?
Mm-hmm.
So it is the change in frequency or pitch of the sound or the color of light that is detected when the wave source and the observer move relative to each other, right?
Mm.
So in other words, we here are the observer or listener, right?
Mm.
And here, the sound, in this case, has moved. So the difference in pitch becomes evident because of that movement, right?
Mm.
So then Doppler effect would be change in frequency or pitch of sound or color of light that is detected when a wave source moves relative or in relation to an observer, or either moves relative to the other. Okay, so when a car approaches, the sound waves are compressed in front of the car, so the waves are pushed in front of the car, but they are stretched behind the car. All right? So they are stretched behind the car. But as soon as the truck or the quantum, okay, so they're
Okay, when it's here, is the sound more audible in the forward or at the back?
the sound is more audible in the back. So those who are behind the car would hear more or a different pitch. Yes. But us, we hear it, but at a distance.
No.
You could hear that something's coming and it's playing that jam by Master KG and Gosazana Dot. Right? And then it passes us. Now we hear it in full swing. So here we would hear it in, I guess, surround sound. But then over here, we would still hear it having, like we would hear the tail end, but the tail end would have much bigger, or rather spaced out pulses.
I hear you.
Yeah. Okay. So we would have short wavelengths here. High frequencies. And this side we would have long wavelengths, low frequencies. Okay, and the long and short of it would be, its formula would be expressed as the frequency of the listener would equal the frequency of the source multiplied by the speed of sound plus or minus the speed of the listener divided by the speed of sound plus or minus the speed of the source. And the plus would indicate for the numerator, the plus would indicate we're going towards the listener. And the minus would be we're going away from listener. Whereas in the denominator, the plus would be away from the source, and the minus would be towards the source. And again, frequency would be in hertz, and velocity would be in meters per second. So we must just note the units there.
Yes. VVS plus equals towards listener minus equals away.
Okay, so we can dedicate now some time to just learning these examples, because I think we've covered the theory, we've talked about a whole lot of other examples and how those are intertwined with a lot of other things that we contemplate, including the supernatural. From fast cars to supernatural stuff. Okay,
I love cars.
Yeah, you seem quite knowledgeable about your cars, eh?
It's from a young age. I started loving cars when my uncle taught me how to change a tire.
Okay.
And then I became more attached to them when my father taught me how to tune an engine. Then, since I'm named after my late grandfather who was a mechanic,
Yeah.
I just felt like it's my sole responsibility to learn more about cars.
Okay. Okay. That's good. That's good.
Plus the fact that my mom used to play me those Pixar's Cars movies, Lightning
Oh,
McQueen.
yeah. I see.
The moment he starts revving up I'm like, yeah, that's Lightning McQueen. So I just adapted to that, and suddenly, I just became an Albert Einstein about cars.
Okay. Now that's good, man. That's good. You should probably consider studying something that has to do with vehicles. So, like a lot of people who would be enrolled for mechanical engineering would be car enthusiasts when I was studying towards a BSc in engineering. So, what would happen in engineering class is that if you're doing first year, it would be civil engineering, mechanical engineering, and maybe electrical engineering students all in one class, because the class size would be like 1,000 people.
Wow.
So half of those would be 3 of those groups like I mentioned, and then the other half would be chem eng and another eng, surveying, etc. Then you'd all be grouped up like that. So we got to see and interact rather with other engineering class members, but they would be from different engineering streams, and we'd often find that car enthusiasts would typically be in mechanical engineering. Yeah, because things like your engines, for example, you would learn things like the 0th law, first, second, and third laws of thermodynamics, which, funny enough, kind of touch on this thing of creation. Like, did the universe get created by a Big Bang, or was it always there? Like, because it's energy, right?
It was actually created by the Big Bang.
It's debatable, because from another perspective, I mean, energy is neither created nor destroyed. So it could be that there's always been that energy. It's just that it's expanded. Maybe
Then,
our observable universe, we've been able to identify that it started at a certain point. But yeah.
What if the world was full of bad people, criminals, all kind of people, and once they're in there, you want to make a clean new world? What will you do? Will you keep the criminals and imbue the new people within those criminals, or will you Thanos again and then create a new world?
We'll talk about that after our class.
Thanos snap that thing.
Thanos snap. Alright, so in our first activity, we've got a sound source that is approaching a stationary observer, and it's moving at a constant velocity. So this is a multiple choice type example. Sound source moves toward an observer, and it's moving at a constant velocity. At constant velocity. So in an exam setting for, say, grade 12, you would come across this type of question. So which one of the following describes how the observed frequency and wavelength differ from that of the sound source, right? So we've got two columns: observed wavelength and observed frequency. And option A is greater than And observed frequency is also greater than.
This water tastes like Fiji.
I think it's because the bottle used to contain concentrate.
You know what's Fiji?
That
expensive water.
Ooh, okay.
One bottle like this, you could spend like 10 grand.
Have you tasted that water before? Where? Who bought it for you?
My aunt, she took me to an event of hers. So like, it was a work thing. And once I got there was this water written Fiji. At first I was like, okay, why is it Fiji? And then people were dashing alcohol with it. And I wondered why. It's just water. But when I drank that now.
Okay. Sounds
as soon as you drink it, it
Mm-hmm.
feels acidic, but then as soon as you swallow it, it's normal water.
Okay.
So I was confused. In the mouth, you can feel it go
It fizzes.
but then when you swallow it, you don't feel that deep fizz here. Yeah, something sharp. No, it's just water.
Okay, that's an interesting phenomenon. Interesting. Anyway, so we want to select the best possible option, right? And what we know from our previous slide is that when we have the frequency of the listener from the Doppler effect equation, the frequency of the listener equals the frequency of the source times the velocity of sound or speed of sound plus or minus the speed of the listener, and this is divided by the speed of sound plus or minus the speed of sound of the source, right? So we use positive on the listener side, which is above. We use positive when the sound source is moving towards the listener, right? And we use negative if it's moving away from the listener.
Or
past the listener. And then on the source side, if the sound is moving away from the source,
it's positive.
Positive, and negative when it's moving towards the source. So now, the observer is stationary and not moving. So we can safely say that the velocity of the listener is 0. The velocity of the listener is 0 because they are not the observer, listener. They're not moving, they're stationary.
I got a question about that.
Yeah.
If you throw your phone off the roof, its initial velocity will be how much?
Will be 0. Or if you throw it?
Yes. Because I know that if you just drop it.
If you drop it, the initial velocity is 0.
Yes.
But if you throw it, it's the amount of velocity that you throw it at. So if you could measure it, then it's that amount.
Isn't it 19.5 ms minus 1 squared?
No, that's an acceleration, and the acceleration that it experiences is due to gravity, and this is in one dimension, vertical projectile motion.
Oh, since the user is not moving, is that a constant velocity?
No, not moving means 0 velocity.
0 velocity isn't a constant velocity because it's stuck in the same place.
It's constant, but the magnitude is 0.
Okay.
It's constant, yes, but the magnitude is 0 because it's not moving. If it were moving, yes, but if you don't know the amount, we just say it's the velocity of the observer, right? So whilst the observer is not moving, the sound source is moving at a constant velocity. So it has a velocity.
I hear you.
So the denominator has got a velocity, that is the velocity of speed of sound is moving toward, minus the speed of the sound source, because the sound source is moving towards. So it's going to be that minus that, right? And then the sound, the observer, it's just the speed of sound, because that one is 0 there. So let's just write the formula again. So it's FL equals FS, V plus minus VL, over V plus minus VS, right? So this tells us that that is 0. So this one is going to be towards the listener, it's plus. And
towards the listener is not plus. Towards the listener is minus.
Wait, it's for the denominator, towards the source.
Which one are we doing? Are we doing the listener or the source?
Remember, we want to establish which one of the following describes how the observed frequency of wavelength differ from that of the sound source. Okay?
That idiot of mine gave me a calculator.
From that of the sound source, right? So we don't know what the values are, but we need to think about what the case might be in this situation. Okay? So what we know from our formula is that with respect to the listener, plus is used when we are considering towards the observer, and negative is away from the observer.
Or past the observer.
And with regard to the source, positive is away from the source, and negative is toward the source.
No, towards the listener. Source, and let me put it simple. When it's a listener, plus is when the source is moving towards the listener.
Say that again.
When it's listener, when we're talking about the listener, his plus symbol is when the source is moving towards him.
Yes.
And then if it's still listener, the minus symbol, it's when it has moved past the listener. The source has moved past the listener. Do you concur?
No, wait.
Here's the listener, he's the cub. Here's the sound. It's approaching. That's plus.
The pitch appears to be higher than the sound emitted by the source, and the opposite is true when the car moves away from the listener. What that means is, if our quantum with school kids is driving this way, the pitch is higher when the sound is emitted by the source.
Don't worry, it's nothing.
Okay. When the sound is emitted by the source, the pitch is higher. Right? It's coming toward us. The pitch is higher.
Yes.
Now, once it moves past us, the opposite is true. So the pitch is lower once it's moved past us and it's moving away from us. Okay. So that means towards the listener, we use positive, and away from the listener, we use negative. So in this case, for this particular problem, which one of the following describes how the observed frequency and wavelength differ from that of the sound source? So in other words, we're looking at, or are we just looking at these two concepts where
I think the answer is D. My thoughts.
Okay, why would you say that?
Well, I just took that from the diagram you drew earlier, that the wavelengths, you see the wavelengths when it's approaching,
Yeah.
they are more together,
Okay.
which means they are less. And then as soon as it passed, the wavelengths increased, which means the frequency is greater.
Fair enough. Okay, so we have to discuss this outside of the formula since we're not calculating any values.
Okay.
You're correct in observing, in spotting that, so well done. So that means if we look at the wavelength, the observed wavelength moving towards the observer should be a smaller wavelength, and the frequency would be great. Okay, so in other words, options A and D fall off. Because there's no way that the wavelengths before or in front of the source could be greater.
Mm-hmm.
There isn't any way that that's possible. So then we're left with just options B and D. I think that's a good observation. Then that means we'd have to now compare between a shorter wavelength in either case because the object is moving toward the source. Frequency, low frequency would mean longer wavelength, but high frequency would mean wait, low frequency. Let's do this.
Dispersed wavelengths.
Yeah, I think D is correct. D is correct.
Because the frequency is nucleated.
The frequency is high.
Yeah. Now you see it.
So we have long wavelengths, but they're moving at a higher rate as the source moves towards the observer. Yes, that's what's happening. So for this type of question, so much mental gymnastics for 2 marks. So much mental gymnastics for 2 marks. Okay. Then which one of the following is the main principle applied when using the rate of blood flow or the heartbeat of a fetus in the womb? I'd say Doppler effect because, I mean, it also uses the same concept where it's checking for, the heartbeat of a fetus in the womb would send pulses.
Hertz.
Would send pulses.
Which are measured in hertz. But then I got confused and it said the rate of blood flow. Like, okay, how can Doppler help with the rate of blood flow?
So when you check your pulse on your wrist or here on your neck, it still pulsates like as your heartbeat does.
But it's weaker.
It's weaker, but it still gives the same type of effect that you're going to measure.
But then if it's weaker and not strong as the heart, like where you can hear it, it's loud. Yeah, and you can feel it when you hold it. Like you have to be in a still moment where you're so calm you can hear it.
You can feel it, yeah.
Yeah. But then if for right you don't feel it, you just declare the guy is dead while he's still breathing. That's a problem.
I mean, we can always discuss, but here's the thing. The point is, the main principle when using rate of blood flow or the heartbeat of a fetus in the womb is that you would be listening out for pulses.
I just wanted to know if blood flow has pulses or not.
Blood flow would have a pulse because it's pumped and circulated throughout the entire body at a certain, according to the rate at which the heart beats. Yeah, so to listen in on that would require principle of Doppler effect. An ambulance. Okay, so we're gonna do these ones, but I wanted to get to do these ones that have these calculations, but it's fine. Let's just do this one here, multiple choice. Not multiple choice. What's it? An ambulance approaches an accident scene at constant velocity, right? Ambulance approaches accident scene at a constant velocity. So the frequency of the source is 980 hertz. That's the frequency of the siren that the ambulance emits, right? And the detector at the scene measures the frequency of the emitted sound. So this would be frequency of the listener, 1050 hertz. So that's the frequency of the emitted sound waves, and that's 1050 hertz. So we must find the speed at which the ambulance approaches the accident scene. So velocity of the source.
I've seen this type of problem. And you know what my friend said? He said that the accident scene will be that I tried to play that game of pushing you in the road and pulling you back, but you accidentally slipped from my grip. Umpenyuri. When I'm about to let you go,
Oh, so in reference to that's such a complicated problem, I'd rather dash.
Hey, it's like he was trying to do that thing when he pushes you then brings you back. Then he pushed you, and when he tried to grasp it, you slipped.
And then you ran away. Okay, so we're gonna assume velocity of sound or speed of sound is 340 meters per second. Okay. And what we must find is the speed of the source. Okay. The detector on the scene is stationary, so then its velocity should be 0. What do you think?
I concur. He's not moving.
Okay.
What breathing technique does he use? None.
And
He's
that
no
would
longer breathing.
That would mean 1050 would equal 980, and that would be 340 meters per second divided by 340 meters per second. Okay, now we have to discuss, before we continue answering, do we use plus or minus?
Okay, let me start with the source.
Yeah.
With the source, we use minus.
We use minus.
Yes, why? Because it's approaching.
It's approaching.
Yes.
Approaching the source.
It's approaching the listener.
It's approaching the listener.
Yes. And
so source is moving toward the listener.
So it will be minus.
Okay, let's use minus. So we don't know that, but that's what we're calculating. So then we'll have 1050 divided by 980. That equals 340. 340 minus Vs. So this would be 340 minus Vs equals 980 times 340 over 1050. Negative Vs equals that 980 times 340, 1050, minus 340. Okay.
Why are we minusing with 340 so many times?
Oh no, in this case we're just applying additive inverses. So that would mean
it hurts my head like a concussion.
That would mean we've got 980 times 340
Vs equals
divided
what
by 1.
Is that in the world? 980.
So we have negative Vs equals 317.3 recurring minus 340. That's going to give us a negative answer. So let's say minus 34. Wait. So we get negative Vs equals negative 22.6 recurring. Therefore, Vs equals 22.6 meters per second. Let's check our answer. So you were correct in guessing
It wasn't a guess.
Or rather, in concluding.
It was a belief.
In concluding.
Yes.
Yes. So you were correct that since we are moving toward the source.
Listener.
The listener.
Yes.
Moving toward the listener. Yes, you're correct. Moving toward the listener. And the thing is, source is moving toward listener, so we use negative. But when source moving toward listener, we use negative. Source moving away from listener, we use positive.
But when the listener is not moving, what do we use?
When listener is not moving, VL is 0.
Okay.
So we just use 340 there.
Okay.
Yeah, when source is not moving, that is 0. But if the source moves toward, we use negative, and if it moves away, we use positive. Oh, sorry. So then it is 22.67 meters per second. Okay. Then the next question is, explain why the measured frequency is higher than the frequency of the source. It is because of that, right? So our source.
So how will you explain that?
So our source is moving toward the observer, right? So as our source is moving toward the observer.
I think I drank one too many cups of water. I really need to use the bathroom.
Oof, okay. You want to go now?
I'll hold it. Let's go.
Okay, because we've got like 8 minutes. Okay. Let's see. Yes, explain why the measured frequency is higher than the frequency of the source. Okay, so we're given that the detector measures the emitted sound waves at 1050 hertz, 1050 hertz. And the reason for that is what we know from the theory of Doppler effect is that as the source moves towards an observer, the wavelengths ahead of the source are shorter and the frequency is higher.
I concur.
All right. And that's why. So waves in front of the moving source are compressed. The observed wavelength decreases. And for the same speed of sound, a higher frequency will be observed. So short wavelengths. So let's just look at keywords. So short wavelengths.
Are compressed wavelengths.
And then higher frequency. And this is because waves are compressed. So those are just our keywords, okay? Then lastly, the principle of Doppler effect is applied in the Doppler flow meter. State one positive impact of the use of the Doppler flow meter on humans. The principle of Doppler is applied in Doppler flow meter. One positive impact of these. This is interesting. I can't think of any right now. Maybe I could, but it's probably not appropriate for learning in class. So in this case, it is to determine whether arteries are clogged or narrowed. So to determine narrowing or blockage of blood vessels. Okay. So that precautions can be taken to prevent heart attack or stroke. So Doppler flow meter measures the narrowing or blockage of blood vessels to detect and prevent heart attack or stroke. And also to determine heartbeat of a fetus to check if a child is alive. Okay. To check signs of life. Or detect heart defects. Okay. I think we can pause here. Magdalene, do you have questions? No questions. Okay. The thumbs down says it all.
Oh.
All right. Yeah. So, but will we be able to see you tomorrow for maths class? All right. Okay. So I think that sums up the lesson today for Doppler effect. And yeah. What I would do is, these are all from Mind the Gap learning guide. So on Google Classroom, you'll find the same learning guide. It's at the top of our...
Okay.
Yeah?
Where can I open my Google Classroom so that I can be able to see all of these?
All this. Okay. That's a good question. So on Google Classroom, so,
Let me
okay.
take the class code.
Yeah, take the class code. It's small I, the number 6, the letter A, the letter T, all lowercase, and then the number 5, and then BB. All right. So you'll just punch that in Google Classroom. And then, yeah, okay, I'll just push that up, move to top. So that it's the first thing that you see.
Mm-hmm.
So learning guide, Mind the Gap for maths, Mind the Gap for chemistry, Mind the Gap for physics is there. So for Mind the Gap for physics, you'll just turn to page... just past it. Unit 5.
81.
What? Unit 5.
Page 81.
Page 81. And that's like 128, like 128 if you're scrolling through, because there's like a whole, like maybe 20-30 pages of just, concepts, what to look out for. So just search page 128. Okay.
From 17.
All right. So, yeah. So we'll end here. Thanks for coming, Magdalene, and thanks for coming, Siamo. I'll see you tomorrow for math class.